these ideas have been around. Have they been well understood? Maybe not. Certainly, I think some of the masters and some of the advanced beings that have walked the earth may have understood them. In terms of physics, in terms of advanced sciences, it's been thought about, but it hasn't been mapped out. It hasn't been understood in its detail in order to be able to apply it to our current physics and our current math. Why would we want to do that, though? Well, we would want to be able to if we want to be able to understand the fundamental structure of creation, and that fundamental structure implies or involves infinities and finite boundaries all at once, we have to find a way to bring these two together, to understand their interaction, to understand how that works. And if we did that, and if we did so, we would have the key to universal forces. We would have the key of the powers of creation. It would be very powerful. It would be powerful for philosophical reason, and it would be very powerful for application to advanced science and technology. Now, it took me a while before I realized that there is a direct and intricate link between infinities and finite boundaries, and how to understand them and how to demonstrate it. I found eventually that the key was geometry, the very thing that got me going in the first place in my geometry lessons. And I'm going to demonstrate to you right now, in very simple terms, that you can create infinities in the confine of a finite boundary. That these are not opposite concepts, but they actually are complementary. There is infinities to create finite boundaries, and there's finite boundaries to create infinities. And in order to demonstrate that, I'm going to use a very simple initial graphic. Although this graphic is simple, it is still absolutely accurate to the geometry that we will see throughout the day today. It's not something in left field. It's something that's very important. So here we're going to do this. We're going to generate a finite boundary we're going to call a circle here. And this circle could be a 3D sphere that contains a very specific space. And in that sphere, or in that circle, we're going to put a triangle, an equilateral triangle. Now, the universe is polarized. And the reason why things are polarized is because they spin. Okay, things in the universe are polarized because they spin. Angular momentum creates shafts of rotation that generates polarity. So if you have polarity, then you can accurately have a reverse triangle in that sphere or in that circle. Now, right away, we have one of the most common ancient symbols that we find all around the world. It's called the Star of David, or the Seal of Solomon, or the six-pointed star. We'll talk about this later on in the presentation, but just take notice of it. Now we can continue to add triangles. And now we get smaller stars, baby stars of David. Okay, baby six-pointed stars. We can continue to add other resolution of stars by adding more triangles. Again, smaller stars of David. Every time we create a new resolution, we can define a very specific boundary. This is very important. And here we find a third boundary, so smaller and smaller sphere. We can continue to make smaller and smaller resolution of this geometry. And in fact, if I give this to my computer as a computer code, and I got it to make geometries maybe 5 resolution deep, and then zoom in, and then go 5 resolution deep again, and then zoom in, and then keep doing that, it would continue to do that to infinity. As long as the computer had power and chips would keep working in there, it would continue to make boundaries for thousands of years. However, I would never, ever, ever exceed the first boundary that I've set for myself. Within a finite system, I've demonstrated to you right now that you can create infinite numbers of division, infinite numbers of sets of information. In a boundary is the possibility of infinite division, and thus infinities and finite structures are complementary. Why is this important? Well, if you were taking these principles and applying them to yourself, you could start to visualize, you could start to imagine, you could start to experience that maybe within the confine of the finite structure that you're in is the potential of infinite division, the potential of infinite amount of information. Philosophically, that has a very powerful impact on someone's consciousness. It just happens to be very similar to what many of the masters that have walked the earth have talked about. That within is God, the kingdom of heaven, infinite boundaries, and so on, or infinite potential, and so on. It definitely has an impact on science. Why does it? Well, I'll give you an example. When we discovered biological cells, we had microscopes that were at the maximum of the power of amplification that we could get at the time, and we thought, my God, this stuff is so small, it's gotta be the smallest thing that the universe does. And then we discovered an atom. And there's billions of atoms in every cell. That is extremely small. And we thought, oh, that's gotta be the smallest thing the universe does. And then we discovered protons, neutrons in the center of the atom. We discovered the nuclei of an atom, and we thought, that is so small. That's gotta be the smallest thing the universe does. And then quarks and so on. And what I'm saying here is that every time we find a new boundary, we think, that's it. We found the fundamental structure of creation. The universe goes to that size and then quits. That's it. I'm done. I'm not going smaller. This is way small enough. We did exactly the same thing in the other direction, right? We thought, oh, you know, at first we thought the Earth was the biggest thing, and then we thought the solar system was the biggest thing. Then we found galaxies. Oh my God, that's got to be the biggest thing, right? And then we found superclusters and so on. Now we're at universal size, and we think, okay, that's it. It stops there. Right? Well, what if it doesn't? Now, what does it mean to the physicist? Well, It means that we've been building accelerators to break particles into smaller and smaller and smaller bits. And now we're at like billions of times smaller than an atom. And we're calling these accelerators, I mean, they're serious pieces of machinery. The one that's being built in Switzerland right now, the Hadron Collider, is costing $300 billion. It took 5 countries to flip the bill for that one. And now we're looking for the X bosons and mini white hole black holes. And I'm like, well, at that point, you're dividing the vacuum. And basically, what I'm saying here is that instead of looking, and I'm not the first one that have said that, famous physicist Jeff Chu said it in the 70s, maybe instead of looking for a fundamental particle, we should start looking for a fundamental principle of division. And that's what I came to, is that instead of looking for a fundamental particle, we should start looking for a fundamental pattern of creation. Because if we understand the pattern, then it doesn't matter at which resolution we are observing the identity. We understand the principle behind the identity. Now we have the key to creation. And that would change a lot of things of the way we do physics and the way we think of the universe and how it creates and how it subdivides. I was really excited about this. I started to really study physics. I started to look everywhere to find how things work and where standard physics was at the time. Where did we go and where did we go wrong and what needed to be changed to make it do that, to make it look that way so that we could find that fundamental structure of creation. I was determined that I was going to find this in my lifetime. It was a big mission, you know. And so I went at it, and I started to study a lot. And now we're going to jump forward to me in Georgia Tech. I'm at Georgia Tech, Department of Physics, with the director there and other physicists, and this is an impromptu private meeting discussion with those guys. And basically my sponsors at the time brought me there to measure up with the biggest and most respected physicists, some of the biggest and most respected physicists in theoretical physics. And, you know, I'm there and they have equations everywhere, and we're talking about things, and it's a very small meeting, you know, but there's a few students, and there's a bunch of physicists there, and there's me. And the only thing I got with me is this book. It's called Gravitation. It's like the Bible of relativistic physics. And it's called Gravitation because when you pick it up, you know, you can really tell gravity is acting upon things. And I was, you know, going through the equations with them, and I'm talking about all this, and I'm really, you know, going through it with them, and I can see that there's a certain amount of irritation, and there's a certain amount of impatience with me because I'm asking very simple, fundamental questions. And everybody there is doing very advanced, you know, string theory physics and all this. And, you know, I'm always going back to like some fundamental things. And they're like, my God, what is this guy doing here kind of deal? And, you know, and so at one point, I pulled out my book, Gravitation, and I said, okay, after all these equations, which is a few thousand equations, on the metrical structure of space and then applied to the universal size and so on. The model of our universe at this point, and correct me if I'm wrong, is that the universe is expanding like a balloon. And I opened the book on page 219 and I pulled it out and I said, here's the picture of what we believe the universe is doing right now. It's expanding like a balloon, and the balloon has little pennies glued to it, and the pennies represents galaxies. That's the standard model. And the galaxies are moving away from each other as the balloon expands. And everybody's like, yes, and that's, where are you going with this kind of deal? Like, if you don't know this, go back and study, come back in a few years. And at one point, well, I'm saying, well, okay, I understand this principle. However, I have a question. Out of all these equations everywhere, what I want to know is where is the equation that represents who's this guy? And the whole room became really silent. And I could see that in the look of the students and the other physicists that there was a look of despair and stress because sweat was a little bit beading. And I could tell that they got worried because they thought, oh my God, this guy, he might just start talking about God, and we're at Georgia Tech in the physics department, we can't do that. and I reassured them very quickly. I started to draw, and I said, well, let's draw the rest of the guy. And what I'm trying to point out here is that in order for the balloon to expand, then the lungs of the person that's blowing into it have to contract. For every action, there's an equal and opposite reaction. Okay? One of the first laws of physics. So if our universe is expanding, then there must be something contracting, there must be some compression happening in order to get expansion. There must be a feedback between the expansion and the contraction. And that was my first clue to the relationship between the gravitational field and the electromagnetic radiation. And as well, it applied to my experience in life. Because really this is all based on my experience in life. When I was 11, I started meditating. My family came in contact with a young master of meditation that was 14 years old, and I was 11. And he taught me how to meditate, and when I meditated, it felt like I was turning my senses inwards and going towards the center of my existence. I was going towards the middle of my being. And I came, out of that, I found a logic in which there was an internal universe and an external universe. There was something going in and something going out, and the two generated boundaries. And that boundary is what we experience as reality. The thing is that in our society, the tendency is to spend a lot of time analyzing what's out and very little time analyzing what's in. Not only in our, social morphs, but as well in our physics and the way we do things. We explode things. That's how we build technology. Our concept of advanced technology is to put a bunch of fuel in a cylinder, put a bunch of people on volunteers on top, and light the bottom and see if they survive the experience, It's all based on expansion, on explosion, on radiation. Very little is based on contraction, on going towards the center, on implosion. And to me, they had to be a direct relationship. So I was really pointing that out, and now we're going to go back to when I was younger, and when I was thinking about that, I could see that this relationship would generate some kind of field equation, would generate some kind of metrical space that I could describe in mathematics and physics that would resemble more like a feedback of creation. Well, just happens that the fractal structures that I was talking to you about when you divide space are based on feedback equations. I went to my first chemistry class, and can everybody see this? And the first thing I asked in my chemistry class is, I want to know what an atom is. The chemistry teacher said that was, not in the curriculum of my first chemistry class. And he said that would be a physics question anyway, and as far as I know, we don't quite know exactly what is an atom, and that was quite disappointing for me. But he knew something about atoms. He said, there's one thing we know about atoms, that they're made out of 99.99999% space. And that kind of blew my mind. I was like, wait a minute. So what we see as creation, all the things we see, are mostly made out of space. But they don't feel very spacious. I mean, it's pretty solid. But what's going on is that there's all these fields interacting, and they don't necessarily are in perfect resonance, and they make boundaries and so on, and so it feels like it's solid, but it's mostly space. It's basically a field dividing the vacuum. And I thought, oh, there it is. It started to match, and that was my first chemistry class. It started to make sense. Oh yeah, maybe we should look at the vacuum. Maybe it's the vacuum, what we call space, that has the key to creation. And the space divides itself, and then we see it as finite boundaries. Maybe the space is the infinity, and the boundary is the finite structure. The field is the finite structure. I started to see it in my head. I got very excited. And later on, I studied vacuum and, understanding of quantum theory, and I realized something. I realized something very important for the evolution of the thoughts I was having. I found that present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formally be infinite, if not removed by renormalization. Now, renormalization is kind of what they tried to do to me at school. It didn't work so good. But what it means is that when physicists start to look with the tools of quantum theory at subatomic particles and nuclear interaction and all this, they found that in order for this to be happening the way we see it happen, the vacuum density at the quantum level would have to have infinite amount of energy. That was the result of the equations. Well, equations that ends with infinity are very uncomfortable for physicists. There's two kinds of technical words in physics to describe infinities. There's one that's infinities that are normal infinities, And that's usually an infinitely small quantity. Two infinities, right? One is an infinitely small quantity, so it can easily be discarded, right? It doesn't really matter. 0.0000 somewhere down there doesn't matter. Okay? That's one kind of. Then there's another very highly technical term you find in physics documentation called nasty infinities. Nasty infinities are infinitely large infinities that creeps up in your mathematics, in your equations, in your conceptual physics. And those are thought to be nasty because when they creep up, it's not like you can just make like it's not there. It's an infinitely large quantity. You can't just sweep it under the carpet and like avoid the whole thing. Well, they did a real good job at avoiding this one. But in general, it was not accepted as a valid theory if your theory breaks down into infinities at its results. And so instead of discarding the concept, they did something that they call renormalization. They used the infinite potential of the vacuum and basically took the Planck's distance and took the 10 to the, what is 1.616 multiplied by 10 to the minus 33 centimeters. So that's a very, very, very small dot. Notice, though, that the 1.616 is very close to the 1.618 of the phi ratio. And they took that distance, like that very teeny point, which is now billions of times smaller than the nuclei of an atom. And they said, well, that is fundamental to creation. And if we put the number of these little dots in a centimeter cube of space, of vacuum, we will have a finite density for the vacuum fluctuations, for the vacuum density, the energy in a vacuum, in a centimeter cube of vacuum. So here it is. They took a centimeter cube of vacuum. They took a Planck's distance, bitty teeny point, and they stacked them into that cube. And then calculated how much density of these quantities would there be in there to get a finite number. The result is 10 to the 94 grams per centimeter cube. 10 to the 94 grams of centimeter cube. That's 10 to, with 93 zeros, you know, following it. It's an extremely large number. When I'm dealing with a number that large and it came from a renormalization, my tendency is to think that we're talking about infinities. Okay? Because if you want to get an idea of what density that means, imagine you have a centimeter cube of space that has all of the stars in the universe condensed into it. Like all of the stars we see with the Hubble. Okay, all the galaxies, everything we see, we just put it all in a big trash compactor and we just squash it all up into a centimeter cube of space. All right? Imagine how bright that would be in one way, but never mind that, then you'd still wouldn't have the vacuum density. You still would be short from the density of energy that is calculated to be in the vacuum at the quantum level. That is a lot of energy, folks. And so, how did this infinite amount of energy divide and create subatomic particle and atoms? To me, that was the question. To me, maybe the vacuum energy had structure. Maybe the vacuum energy wasn't just a random fluctuation like this, but had a boundary fractal structure, had a geometric structure to it. I didn't know why at the time. I didn't know how I could prove that. I didn't know how I could describe that. But I wanted to explore that thought. I started to see that maybe, just maybe, everything we see in the universe is just division of that energy density of the vacuum in various scales. To me, there was some logic to it.